Well, I'd like to welcome all of you back this afternoon when we continue in this interesting exposition of focusing on today what it's like to explore, okay? And we have a very exciting panel discussion for you here this afternoon. I'm Maria Zuber. I'm a professor of geophysics and head of the Earth, Atmospheric, and Planetary Sciences Department here at MIT, and I will be moderating and speaking this afternoon. Buzz Aldrin, we decided that being on a panel with many other astronauts could not possibly give him the opportunity to impart sufficient insight that he has from his career of exploration. So we're delighted that he will be talking more to us this afternoon. We have Steve Squyres, who's the Goldwin Smith Professor of Astronomy at Cornell University and, has done a number of different things. He's an investigator on Mars Odyssey, an investigator on the imaging team of Cassini, but is probably best known as principal investigator of the still-going Mars Exploration Rover mission. Still going, how many days of the 90-day mission of 2581, so he has something to say about longevity, I'm sure. And James G. Bellingham, who's the chief technologist of the Autonomous Ocean Sampling Network.Program of Monterey Bay Aquarium Research Institute. Okay, so we will also be having, at the end of the 10-minute presentations here, we have a video clip from Cady Coleman from the International Space Station as well, who obviously could not be with us personally. So, okay, so people ask me what it's like to be an explorer, and I'll tell you, I feel so blessed to be able to do what I do for a living. And it's just, I feel remarkable that I get paid to do it, in fact. But when people say, what's it like and how do you spend your day, it's actually a little bit worrisome because what I do, I talk on the phone, I make PowerPoint presentations, and I fly on airplanes. And that's most of my time. But I explore the solar system, and currently I'm on 5 active robotic exploration missions, which does a great job of filling the hours at a day. And I thought I would just take a couple of minutes here and just talk about one of them. And basically just show you some pictures. This is for a mission called GRAIL, the Gravity Recovery and Interior Laboratory Mission. This is a spacecraft mission, well, a dual spacecraft mission. We're going to have 2 spacecraft that will be launching to the moon. The launch window opens September 8th of this year. Many of you will be invited to the launch. If you'd like to be invited, let me know. We'll put your name on the list. This is MIT's first PEI ship in a full space mission. So I thought I'd tell you just a little bit about it. Okay, so here are the 2 spacecraft, and actually in the exposition over where you had lunch today at 5 o'clock, Lockheed Martin kindly sent out some models of the 2 spacecraft, so you can see them. They're not quite to scale size, but they're about the size of dishwashers. So they're very small spacecraft, and some people like big spacecraft, but I like small spacecraft because launch cost per dollar. They're very inexpensive. So these 2 spacecraft will be launching to the moon on the same launch vehicle. They will take about 4 months to get to the moon. They will insert into orbit around the moon on New Year's Eve and New Year's Day of this year, keeping with the NASA tradition that all critical things happen on holidays so that people have to work, okay? And there are reasons why we're actually doing that they're actually quite sensible, which I won't go into. And these two spacecraft, they're going to be in polar orbit around the moon, about 50 kilometers above the surface, and they will range to each other, and we will range to them from Earth at different radio frequencies. And by looking at small variations in the velocity between the two spacecraft, we will determine the gravity field of the moon better than we know the Earth's gravity field. So here is a picture. I like hardware, so most of this presentation is hardware. This is one of the antennae on the spacecraft, and these two spacecraft will range to each other and determine the velocity of one spacecraft with respect to each other to a couple of tenths of a micron per second. So what we're doing actually isn't very hard. It's just that we need to do it pretty well. Okay, this is a lot of flight hardware. And actually what I wanted to do by showing this picture is just to convey the fact that while this spacecraft is unusual for NASA spacecraft in that it doesn't have a whole suite of instruments, it just has one instrument per spacecraft, but that there are a lot of components associated with doing a spacecraft mission, and that every single thing here has to be done perfectly for this to work. Okay, so if you want to range to a couple of microns per second, it's very precise. So I want to point out this one. This is a reaction wheel assembly right here, and it's about this big, and this has given me more problems than you can imagine. And if you can see this here, this is a picture of the celebration when the reaction wheels from the company were delivered to NASA. And this is Goodrich Ithaco Company in Ithaca, New York. Steve, maybe you know some of these people, but look at how they're dressed. This was an extremely, it was supposed to be a small modification of something that we knew how to do, and it turned out to be a real research project. And we had some outstanding technicians and engineers who had to actually engage in acts of nothing short of heroism in order for this to happen. So when they made the delivery and these devices worked extremely well, there was a great celebration, which was well deserved. So here are some pictures of two of the spacecraft. The spacecraft are being built out at Lockheed Martin in Denver, so you can see them here full size. Here's one of them, and here's this one in the foreground, and then the other one being worked on in the background. And as I said, they're very small. If you see me bolt out of here tomorrow afternoon, it's because I'm heading out for yet another review. I have at least one review a week because these two spacecraft are being delivered to the spacecraft to Cape Canaveral in May. Okay, here are the most important thing that you do in robotics is test, 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 test. And so here are just some pictures of our team in testing the variety of components on the two spacecraft. Okay. Here is a picture of the instruments being loaded on a plane out in Pasadena, and they were flown to Denver to be put on the spacecraft. And this is just a placeholder to say that when the two spacecraft get sent to Cape Canaveral, that I'm going to be in the cargo plane with the spacecraft, and they're, managers were telling me, Maria, you don't have to do this. We can just send them out there. You can meet us in Florida. And I said, they're my spacecraft. I'm delivering them to Cape Canaveral, and I'm landing on the shuttle landing strip, and no one else is delivering these. And I was talking to Steve Squyres at lunchtime, and he said he did the same thing with the Mars Exploration Rover. So you tend to feel very, very attached to these things. Here's my rocket. I'm very excited to have a job where I can say I bought a rocket, and I bought this one, and I had my choice. I got this picture, and actually on the same day that I got this picture, I got a picture of a fuse board that melted in testing. And I decided to show you this picture because I thought it was a lot more uplifting. But the fuse board has since been repaired, and we have no issues there. But in case you get the false impression that this is simple, here's our launch pad here, and I just want you to know I have a folder on my computer with about 40 emails on it concerning the design and the font of the name of the mission, okay, and you will, it has never happened before that the name of the mission is in the same font, the same size font as the name of the rocket, okay? So it took 40 emails for this to happen, but we persevere, so I was unwilling to settle for a smaller font, I'm pleased to say one of the things I want to talk about is outreach and how what we do is so exciting that it engages students who have talents in critical and analytical thinking, in mathematics and science and in technology, that these are endeavors that are worth study. And so I'm always thinking about new ways that we can get students involved in exploration. So I said if I ever won a mission, I was going to do this properly. So I immediately went to Sally Ride, America's first woman in space, who devotes her career to getting students involved in, particularly middle school girls, keeping them interested in math and science. And so we have 4 camera heads on each spacecraft that have no scientific purpose. They are on the spacecraft totally to do outreach, where students at schools will be able to program images so they can take their own images of the moon. And Sally has done something similar with something called EarthCam on the space station. It's been incredibly successful. But I think the public deserves ownership in space, and kids are awfully smart, and it doesn't take a whole lot to get them motivated to go in and figure out how to run the software so that they can program images to take pictures of the moon. And I just want to end here with a nice picture of the moon over Cape Cod. And imagine what it's like to be sitting on the beach and to be able to look up at the moon and to know that you have made observations where you have gained understanding of the moon that no one else knows for a short period of time. It's just an amazing feeling, and it's something that never gets stale, and it drives me, and it motivates me, and it's a wonderful career to have, and I'll end right there. Thank you. Okay, I'm now going to ask Steve Squyres to come on.
Well, thanks, Maria, and could I have my first slide up? Anytime you get invited to participate in an event where the words "the future of" appear in the title of the event, I think it's wise to approach it with a certain amount of humility and trepidation. In my normal work, my everyday work, I'm used to, as Maria mentioned, working with instrumentation that looks something like this. In order to prepare for today's event, however, I've had to familiarize myself with a different form of instrumentation. And so what I'm going to try to do for the next 10 minutes here is gaze into that crystal ball and give you sort of some thoughts on what the future of space exploration, and I'll be focusing largely but not exclusively on robotic space exploration, might look like. Now, my crystal ball for the next 10 or 20 years is maybe not too cloudy. One of the things that I've been participating in recently is something called the Decadal Survey, which is something that NASA does every 10 years with the National Research Council to plan the next decade or two of planetary exploration. So the first couple things that I'll be talking about actually sort of come from that Decadal Survey and are plausibly actually going to happen. The first of them that I want to mention is the very challenging task of returning rocks from the surface of Mars. We have learned so much about Mars with the spacecraft that we have sent there in the last 10 or 15 years that we've reached the point where the next big increment in understanding is going to come from bringing rocks back from the surface. Now, to do that, you got to do a bunch of things, and the plan is to actually break it up into 3 missions. The first mission, shown at the upper left, is a rover, a bit bigger than Spirit and Opportunity, that would drive around and collect a cache of rocks and take those rocks and put them in a container on the Martian surface. The second mission, shown at the right, lands near that cache, picks it up, puts it into the nose cone of a small rocket, and launches into orbit around Mars a spacecraft the size of a coconut that contains those samples. The third mission, shown at lower left, goes to Mars, goes into orbit, finds that coconut in space, puts it into a sample return canister, and sends it back to Earth. This is an incredibly challenging suite of missions, but what it will do is it will return a set of samples that can continue to provide good science about Mars for decades into the future. Another one that all of us in the planetary science community are extremely excited about is Europa. Europa is one of the moons of Jupiter. It's roughly the size of the Earth's moon, but it has a crust of ice on the outside, and there is good reason to believe that beneath that crust of ice lies an ocean of liquid water. So we got 2 possibly accessible oceans in the solar system, one here on Earth, the other one on Europa. And one of the missions that we're looking at is a mission that would go and orbit Europa with a number of instruments, including a long wavelength radar that can see through that ice, tell us how deep it is to get to the water, tell us where the thin spots are, tell us where are the places where you might go and land. And the thing that's exciting about Europa is that, of course, with that ocean being present, it's conceivable that down on that sea floor, there could be hydrothermal vents, there could be the kind of local environments that support life at the bottom of the Earth's oceans. Another exciting place is Titan. Titan is a moon of Saturn. It's a huge thing. It's like the size of the planet Mercury. It has a dense atmosphere of nitrogen. The atmospheric pressure at the surface of Titan is higher than it is in this room. And it has an active hydrological cycle where it rains, and there are rivers, and there are lakes, except it's not water. It's liquid methane and liquid ethane at temperatures of 80 or 90 degrees above absolute zero. So it's a fantastic world, and it's the kind of place that you can use rather familiar forms of transport to explore. You can fly a balloon in the atmosphere of Titan. You can sail a boat in the methane-ethane lakes on the surface. You can do submarines down at the bottom of those lakes. So Titan is going to be a fantastic place to explore as well. Now, once you look further out into the future, that's where my crystal ball grows a little more cloudy. But let me tell you about some of the things I'd like to see happen. I talked earlier about Europa and the idea that there's an ocean of liquid water and that we can find where the thin spots are. Well, the obvious thing to do next is to go into that ocean. This is a phenomenally difficult mission, and this is going to happen decades in the future. You have to land. Then somehow you have to get through, I'm going to wave my arms and guess, about 10 kilometers, maybe, of ice. Maybe you melt your way through it. And then when you get down into that water column, you've got 100 kilometers of water between you and the seafloor, which is where the interesting science is. So you need some kind of autonomous underwater vehicle that can swim down to the bottom of that ocean, and in the vastness of that ocean, find the interesting spots and explore them. And then somehow get the data back. And all of this has to take place on a moon that is embedded deep in the Jovian magnetosphere with a hellaciously difficult charged particle, energetic particle environment at the surface of Europa. This is a very, very, very tough mission. I hope it happens in the next 50 years. Here's another one, Enceladus. Enceladus is a fantastic place. It's, again, one of the moons of Saturn, but it's a tiny little thing. It's only 500 kilometers in diameter, and yet despite its small size, and you would expect its very cold temperature, there are geysers, literally geysers of water that are erupting from the south pole of Enceladus. And we know this from the Cassini spacecraft having flown through it. And there's not just water. Okay, there's organic materials being erupted in these things. What is in those vents? What is in those fractures? A mission I'd love to see, you can see at the upper left there, this is the kind of collector system that you might fly if you could fly a spacecraft through the plumes from one of those geysers, and then again, return samples to Earth and figure out what's going on inside of Enceladus. Now, I've talked so far mostly about robotic exploration. Obviously, there's a great future for human exploration as well. And when you look at it realistically, the three kinds of objects you can see humans going to in the foreseeable future are the moon, asteroids, and Mars. Let me express my personal view on that, on this, and that is that I believe it makes sense to send humans to the places where humans, because of their unique capabilities, contribute the most. And humans contribute most, in my view, in complex environments. The more complicated, the more difficult, the more unpredictable the environment, the more humans add to the mix. And when you look at those three classes of objects, the moon, asteroids, and Mars, the one that stands out in terms of its complexity, in terms of its potential for humans to contribute the most, is unquestionably Mars. Mars is far more complex than the moon. Mars is far more complex than asteroids. Mars is the place where humans make the most difference. And so in my view, the future of human exploration should be focused towards getting to Mars. That doesn't mean that you can't make sensible stopping points along the way. Okay, there may be places where you have engineering milestones or development milestones like the moon where you show your capabilities before you go on to Mars. But to me, for humans, Mars is clearly the target. Okay, so now looking way downstream. I'm going to look 150 years into the future now, and maybe more than that. To me, the real frontier is planets around other stars. This spacecraft here is Kepler. This is a spacecraft that is observing a patch of sky in the constellation Cygnus. Here's the piece of sky that it's looking at, just a little part of the sky. And what it's doing is it's detecting planets around other stars by looking at the tiny dips in the light curves from these stars when the planet passes in front of the star. The spacecraft's been up there a little while. They've been staring at stars for a while, trying to find planets, and here are the planet candidates just in that tiny patch of the sky. There are lots and lots and lots of worlds out there to explore, and the blue ones among these candidates, those are Earth-sized. So I think the most exciting thing that we have in the future of exploration is to study these worlds. Initially, it will be from our solar system, looking out with ever more advanced telescopes. But the thing that I look forward to in the very distant future is actually sending spacecraft to planets around other stars. It's going to happen. It will first happen robotically. You can think of a number of technical challenges that are associated with doing something like that. Certainly communications is going to be a challenge. Certainly autonomy of your spacecraft, when you're talking about spacecraft that are light years away, having those spacecraft operate completely autonomously in very poorly understood environments will be key. But the toughest problem, the singular problem that must be solved before we can ever think about traveling to other stars is propulsion. I heard antimatter mentioned earlier in the discussion before lunch. I think that's quite possibly going to be the way to go. And for all you smart young students at MIT, if you want to make your mark on the future, one thing to think about is how to develop a propulsion system that's going to get us to other stars, because that's the thing that excites me most. Thank you.
Okay, we'll next hear from Buzz Aldrin.
Thank you for such a long introduction. Whoever's controlling the slides, could you go to the one that show? Oh, I don't know. I point this at you guys out there. All right, this. I talked about this a little bit earlier. This is what I call a comparison between the direct landing on the moon and what we actually did. The rocket that Wernher von Braun wanted was the Nova rocket, 9 engines, and on top of that, they'd have a propulsion system and this sizable spacecraft. The Nova rocket wouldn't be ready in time, so he could split this up between this spacecraft and the TLI stage, translunar injection, the upper stage of the rocket that would send this spacecraft. And an MIT doctoral candidate who works with Ed Crawley did the size measurements of this just to put a point across that to send a multi-purpose, that is my name for this big monstrosity, because the crew would be launched on it, it would go to the moon, it would do its landing, support those activities, then come back and land in the ocean. No separate specialized spacecraft at all. John Houbolt based his suggestion and doggedly pursued it and has been my role model, so to speak, for quite a while. He said to the folks at NASA, now if you specialize the spacecraft and have a lander kind of like this and put it on one Saturn V along with the command and service module, you only need one Saturn V. So get that, 2 Saturn Vs for one spacecraft to the moon and back, multi-purpose. Specialized spacecraft, 2 of them, only needs one Saturn V. That's a big deal. And I just want to point out that just don't say, well, we went to the moon with lunar orbit rendezvous and it was better than Earth orbit rendezvous. The big difference is multi-purpose, and that's exactly what the Senate and the Congress want us to build and mandate it, that we build a multi-purpose from the surface of the Earth to Earth orbit, and then from Earth orbit all the way to Mars or asteroids or whatever else, and all the way back, and it lands in the ocean. Of course, we do specialize the lander, whether it's on Phobos or Deimos or the surface of Mars. Well, and not actually for the moons of Mars. We could use an Orion habitat. Let me just develop a little bit for you engineering folks out there. if we want to send a specialized spacecraft, or plural, a long distance with high demands on reliability and long-term life support, we can put all of that in one big, large spacecraft. But now compare that with two medium-sized, about the same size, medium, and we avoid single-point failures as much as possible, but something happens and knocks out one of those medium vehicles, we still have the other one. Now, let's take those two medium, and one gets smaller and the other one gets bigger until the small one disappears, and you were back where we started from with one big one. Now, somewhere in that trade space is a more optimum, and I don't think it's two the same size. What you'd like to have at either Earth or at Mars is an Orion taxi, and you'd like to have an Orion HAB, but not an Orion that's government, that lifts off from the surface of the Earth and goes into Earth orbit and then does some of these others. That's a government spacecraft, and it's not going to compete well with the civil spacecraft, especially when it's a copy of Apollo that goes all the way to the moon and back. Because when we go to the moon, or according to the Constellation program, we were going to go there for at least 6 months, and that spacecraft was going to stay in orbit unmanned until the crew lifts off again, and then they come home. So it doesn't have a crew in it. Now, the Constellation program, as I see it, originated from a desire to quickly copy what we did in Apollo. But it began to deviate from that when the accident board opened the door, accident board of Columbia, by saying, separate crew and cargo. Now, we could have just done that and put it on some rocket, but instead, we wanted to put a small rocket, and it's my contention that ATK lied when they said a 4-segment solid could do the Ares 1 mission. They had been trying to sell the 5-segment solid to the Air Force for quite a few years, and the Air Force just wasn't interested. So they said, okay, we can get a command module or an Orion to rendezvous the lander somewhere in Earth orbit, but the Orion is going to have an upper stage on a 4-segment solid. Well, it wasn't long before that obviously wasn't going to work, and they put the 5-segment solid in there, and even that wasn't enough. When you look at Orion, you should ask the question, why is a service module with fuel so small? Well, because it doesn't have the capability of putting the lander and the CSM, or the Orion, into lunar orbit. You got to put the fuel in the lander. And that makes the rocket even bigger, and the lander is just gigantic. Not quite this big. All right, now, this is kind of a quick unified space vision. Now, this is what I presented to the Augustine group. This is a modification of it, but what it really shows is the ability to kind of start out in 2010-11 and proceed around the clock this way. When we first constructed this, the guy that constructed it knew that orbits go this way, so we had the thing up here going this way, but that isn't the way a clock goes, so we rearranged it with the potential. This is the 50th anniversary of the lunar landing, and we reaffirmed that we're on the right path, and we do various missions. The first thing we've got to do is to develop really a long-term life support system. We do that at the space station. And then we have a prototype of the Orion HAB, and then we start flying them along with the Orion taxi. And we can do that in low Earth orbit, and then we can cycle missions back and forth between the Earth and the Moon, demonstrating what could be done in a private spacecraft with cycling orbits between Earth and Mars for adventure travel. We're doing that to check out the spacecraft under varying conditions over a period of time, and then leaving the HAB module at either L1 or L2. Let me move to the next one that we, maybe I'm gonna have to go back this way. All right. Hopefully you can see this. This was put together about 2 years ago, and I was hoping that the last 5 shuttle could be delayed a year between the missions, and so that we could, between those year missions of the shuttle going to the station, 3 months before and 3 months after are occupied in getting ready and checking out after the mission lands. So you have about 6 months in between, and I felt that the workforce could be working on the next lifting body runway lander that would start to fly along here. And this shuttle launch system would be evolved into a direct type, which at the time I prepared this is what I felt we probably ought to do, the quickest and the cheapest. When it began to look like we were also going to study liquid rocket boosters, not being a real friend of solid rockets at all from the very beginning, I kind of changed my approach and wanted to retire the orbiter as soon as possible and transfer over to launch vehicles. And I think a lot of people convinced me that the cost of doing this sort of thing just wasn't going to work. So we have a test bed at the space station, and then the first exploration module is more of a prototype. Then we start flying in Earth-Moon cycling orbits around 2017, 18. We retire one of these in low Earth orbit for refueling, and another one at L1 and L2. There's a comet, and I think the next advanced mission is a 1-year orbit where you are on a free return trajectory whenever the engine might cut off, and it's kind of a simpler than rendezvousing with an asteroid. And there is this comet that we could fly by at this term, Vintanen. Then there are 2 asteroids, 2001 GP2. There are many others that could be in here. And then Apophis. I'm sure that you know Apophis is the asteroid that at first tracking, it looked like there was a fair chance that it could impact the Earth in 2029 on Friday the 13th of April. Further refining of the orbit looks like, well, that's probably not the case, but it could also go inside a geosynchronous orbit, and the probability of distance inside geosynchronous has a keyhole in it, and if it goes through that keyhole, it's going to raise its semi-major axis from being below Earth's orbit and moving in a catching up way to above Earth's orbit, and so it's Earth is catching up to it, so that in 2036, Easter Sunday, April, this would impact the Earth somewhere between northern Japan and down the California coast to around Panama. And the middle of that is maybe 200 miles off the coast of California, with 150-foot tsunamis. Now, actually, obviously, we don't want that to happen. But we can make a pass by Apophis in about 2021. The next thing we'd like to do is to land a habitat, an Orion HAB on Phobos, and then check that out while we're sending a human mission to occupy that. I've selected 3 year-and-a-half missions of 3 mission controllers or communicators with the robots that are sent to the surface of Mars in this 1.5-year period. And then this crew would go there, come back. The second crew would go and do the same thing, come back. And the third crew would go there with the lander and land maybe a week before the 6 people come from the Earth, and make 9 people occupying the Mars somewhere between 2031 and 2035. Having these sequence of missions progressively getting more and more ambitious is going to keep the interest of the public up, and I think result in more and more challenging opportunities. Everything in here can be slid synodic periods of Mars. I'm getting the hook, I see. So I'd be happy to answer questions on this and other things like travel to Alpha Centauri. The book being made into a movie is called Encounter with Tiber.
Great. Thank you, Buzz. I'm sure there will be questions about this. So I want to remind people that there will be smiling people sending out index cards for your questions that we'll take. Our next speaker is Jim Bellingham.
Well, to whoever scheduled me to go after this vision for exploring the solar system, I'll talk to you later. I'm going to take you back to Earth. I think you heard sort of an introduction to exploration of the oceans from David Mendel this morning, and I'm going to talk a little bit more about that and give you some sense of what I think are the challenges for the future in this domain. And I think that to a large degree, this is really shaped by my personal experiences. When I listen to the early exploration of space, to the Apollo missions, I listened to it via sort of a squeaky shortwave radio Voice of America broadcast in developing countries, mostly different parts of Asia. So when I came to MIT, I came here having spent about 2/3 of my life overseas. And so I kind of came into this with a very strong sense of exploration, a very strong sense at the same time that there are enormous challenges that we need to solve as part of those exploration problems. And I always felt that sort of posing them as sort of either or was kind of missing the point. It is true, however, though, that for those of you who are in the audience who are students, you're on a world that is quite a different world than the one that I grew up in. There's 7 billion people on the planet today. By sort of the 50-year mark here, maybe we'll be coming down from 11 billion, sort of in 2050. That's kind of an optimistic perspective. And I think that really shapes, in effect, how we're going to approach this exploration problem, because it's going to shape the problems we take on. So that's what I want to do. I want to talk a little bit about some of the problems I see being posed for us in the future, and how exploration is part of the solution. So first of all, I think that it comes as sort of no surprise to people in this room that the Earth is changing. I think that in particular, most of the Earth, the least understood part of the Earth is the oceans. There's a picture of high latitudes, part of the world that I'm particularly in love with, but a part of the world which which is changing most dramatically. You're probably familiar with stories of the ice cover in the Arctic gradually disappearing. And just to give you a feeling how little we know about that, where I come from, in Bari, we're out in the West Coast in Monterey, we have 2 submersibles, deep diving, remotely operated vehicles that spend about 300 days a year at sea. A lot of it in the vicinity of Monterey, and we've seen about 2% of the seafloor in Monterey Bay. That's probably the best explored patch of seafloor in the world. When you look at the Arctic Ocean, it's basically unknown. Indeed, it's closed to us for a good half of the year. The other piece of this is that we're industrializing the ocean. So peak oil in the US was perhaps, in the continental US, was perhaps in the early 70s. North Sea oil has peaked now. And this is just one example. It's maybe an early example of where, as we deplete the terrestrial resources, we turn to these other environments. And exploration has a very, it has a connotation which is linked directly to our prosperity, and indeed to the prosperity of the world. And this is an issue which I think threads across a number of different types of resource. So, for example, here are fishery landings. That upper left-hand corner you may not be able to read. That's a map of the world. Those colors show the fish landings in 1958. And then you have down there in the lower right, in the much cooler, much lower numbers, fish landings in 1999. And the basic story here is that we're much better at exploiting the environment than we are at understanding it. And of course, if we don't understand it, we can't really manage it particularly well. And the ocean, we really don't understand at all. So as a consequence, rather than calling it risk mitigation, we might really call it, in this case, survival. Why do I say that? Well, an interesting number is that something like, well, a little bit less than 20% of the animal protein we eat comes from marine animals. And the Economist says that we're doing a job right now of producing about enough food to feed the world. The problem is agricultural production is producing by about 0.5% a year, while food production is increasing about by 0.5% per year. And you can see here we're really depleting in unsustainable ways a lot of the resources, largely because we don't understand. So what is the challenge? And I thought I would just put this down in black and white, because until you put it down, you can't really solve it. So humans are expensive in remote and hostile environments, and that's true because we require the equipment and consumables to keep us alive. It's expensive to transport us, our equipment, and our expendables. And so if you look at this, to me, the question here isn't whether or not you should send humans to these remote environments. I think that's part of who we are. We will go, we must go. But the question is, how do we make it affordable to get there? And I think that that's where robotics, in particular, has a particularly large role to play. So I've been building marine robots for quite a while. I did my early development work here at MIT. That's one of our vehicles there. We called it Squyres. So I started this back in the late 80s. And that vehicle could go a few kilometers. It really carried almost nothing in the way of sensors. And in between that and my current vehicle, there's a lot of other vehicles, some of them very big and very deep rated. But I'm particularly proud of that new system. It has a range of perhaps 1,500 kilometers, or perhaps 4,000 kilometers, which is enough to get from California to Hawaii. And it has all kinds of sophisticated sensors on board. So the story here is really that there's a very rapid rate of change in robots, in marine robotics, in just a matter of a few decades. And I think that change is going to accelerate. Part of it is that we're learning how to use them much better. So here I am at MIT. I have to put up at least one equation. But being a physicist, I'll set most of the terms to 0 to simplify it. So this is just sort of to give you a feeling for when you're working in the ocean environment, what's the energy problem that we're up against? And we kind of divide our energy use of our vehicles into 2 terms. How much does it cost us to move through the water? And of course, it's a very viscous medium, so it actually costs a lot of energy. And then how much power do we spend on everything else? Now, the propulsion term actually goes as velocity cubed, so there's a v cubed there. And so you can ask the question of, if I want to map a particular patch of ocean and I have to get it done in a certain amount of time, what's the total amount of energy it's going to take me to do that? And so if I have that one vehicle there and it takes me a time tau, you can see that first equation, E1, that's kind of defines, in effect, my reference term of how much power it'll take. Now, the thing is, if I put two vehicles in, what happens is the power, and by the way, I've set hotel load to 0 there, just because we usually do spend most of our power on propulsion. If I set the hotel load to 0, and then I halve the speed, but double the number of vehicles, basically what you use is you use a quarter of the energy. So this is kind of the big lesson, and if you go all in the back room could start this, this little animation. This shows sort of circa 2003 how we started running our field programs using larger and larger numbers of robots. So this is a picture of Monterey Bay. There's that cool water, which is upwelling water, nutrient-rich water on the surface. And underwater, now this is an animation, but this actually happened. Actually, there were more vehicles in the water. What you have fleets of underwater robots, which are all actually going comparatively slow, but collectively give you this enormous measurement capability in the ocean environment. So increasingly, we're using these many-body methods for observing the ocean. And I think this is part of the larger trend. So Dr. Aldrin talked about specialization. I believe very strongly in specialization of these robotic capabilities. And I think that the frontiers of robotics are increasingly moving to how we use these systems together cooperatively and what the appropriate specializations are. Because we need an infrastructure for energy, for raw materials, for processing, perhaps manufacturing, for transport, for maintenance. Robots become a lot cheaper to develop if you can count on being able to fix them. And that graph there just shows for one January where most of the sunlight is. And notice that most of the sunlight in this particular January, occurs over the ocean. So this is one of the cues. We have to learn to use the environment better. Now, being a technologist, I do spend a lot of time just worrying about what are the general technological trends. And I think this is kind of an interesting graph here, because what you can see is that some things are going up tremendously, rapidly, or exponentially. And so those are the classic ones: CPU speed, disk capacity, memory costs are all up in there. Other things like battery power aren't increasing so quickly. And so what you can kind of think about it is, this is the platform capability here, because you're really limited by energy, onboard energy. And then this is what you can do with the platform, because it's in some senses a function of what processing power that you can put on it. And so this is sort of my vision. This is sort of what gives me hope for robotics. Surely there are nonlinearities in here somewhere as we learn how to use this processing to make better robots. But I see sort of, in effect, the capability per kilogram is going up quite dramatically in the future. And I think it's the job of the people in the room here to make that happen. So finally, I just want to say that although I've argued here that robots are in effect enablers of human exploration and human and in effect human prosperity, I also think it's true that robots give us an opportunity to go to places that we've never been before. And so I'm reminded of that movie, The Fantastic Voyage, where people got shrunk down and inserted in the bloodstream of a human being. And I think that in some senses, robots let us do the same thing. There are some places we simply can't go because we're too big or whatever. And robots, in effect, give us a way to be there. So I just want to thank, finally, the MIT folks for having put this on and having included me in this event. And with that, I think I'll turn it over to you, Maria.
Okay, Jim, thanks very much. Okay, in a second here, we're going to roll the video from Cady Coleman, who will be reporting to us from the International Space Station. I'll remind you that we've got some folks with index cards here that you can write down questions if you're interested in questions, and we'll pick those up after we hear from Cady.
Hello, and welcome to the International Space Station. I'm Cady Coleman, NASA astronaut, MIT graduate from 1983, and this is my world, at least for the past few months and another month. Really happy to be here with you today and to share this place with you. I'm very privileged to live aboard the International Space Station and commute to work here every day. And I love pretty much every single minute of it. I feel very privileged to be here and to be part of this symposium. I'm actually really excited to know that all of you are together. And I had just a few things I wanted to share from this very unique vantage point. In the view outside from our cupola module, which has windows on all sides and allows us to see marvelous places, you know, coming and going, and also just gives us that perspective of looking down on the Earth and realizing that we are in an orbiting spaceship, and that when I look out at the stars and I see, you know, so many stars and planets, and know that, you know, we have a place in the universe, and it's in part of our job is to explore that place. So I'll ask you today two things. One is to congratulate yourselves on being part of exploration. It's part of the human spirit, and if you're in this auditorium, then it's something that you have a passion for. And second, I ask you to realize that if you're part of the present, then you're part of the future. Whether it's to continue engineering efforts to explore beyond our Earth, or whether it's to educate the younger generation who will then be carrying that torch for us. All of us are part of the future when we're part of the present. And I'll just ask you to enjoy every minute of the symposium and make sure that you meet some people, let them surprise you, find out what kind of skills they bring to the team. And I hope all of you manage to increase your teams by at least a few people and think about a few things you haven't thought about before you came today. What I think is actually just pretty neat is it's not a question of whether an MIT alum will be up on the space station. It's a question of which MIT alum is up on the space station right now, and which MIT alums will be there in the future. You know, we could take that one step further, and we could celebrate all of the MIT technology or MIT-inspired technology that made this space station and that we find up here now in the experiments that we do. But I don't think I would have enough satellite time to be able to name all those things. All of you play a part, and we need everyone with their very different talents, and we need to bring up our children to recognize and celebrate the differences among us and realize that it is bringing those differences to a team that allows us to pursue and succeed in large endeavors like having it become normal that somebody's mom lives on the space station. I think that a place like MIT is really good at trying to make sure that they develop the whole person, and that's part of this exploration as well. We need to have people that are part of this that are the technical and scientific and engineering people that make maybe the physical steps happen. But we also, in order to actually do those things, we need people to be able to communicate, to sell those ideas, literally, to be able to write about them, to share them, to portray what's happening and what will happen. I'm living here on a space station. I'm one of a crew of 6. We all have different hobbies, different interests. We bring those to the space station. I myself play music. There's others that are singers here. We've got some that like to paint and like to draw, some that like to write. And all of us bring our different talents besides the engineering and the science. And I think those are so important to an exploration. You know, I'm actually, married to an artist, and so it's always fascinating to me to see the mixture of art, science, and technology that make his work possible. And people actually give us a hard time because he makes glass planets, and I like to go look for planets. And but if you take a look at work or like his or other people who portray distant worlds and the future, and by being artists and showing it to us and making those visions real to us who are more the engineering types, then we actually have a vision that we can pursue. We have a vision that we can share with other people and manage to get the resources that we need to pursue those dreams. So realize that it takes lots and lots of different kinds of people to make up exploration, and that it takes very many small steps. It takes many large steps as well. And some of us are part of each of those kinds of steps, and together we'll explore. In closing, please enjoy the symposium. It's great to be celebrating MIT 150 years of education, of excellence, of exploration. Make the most of this opportunity to be together. And I do wish I could be there in some ways, although I will tell you I'm very happy to be here. And in the energy and excitement that I know is being generated at this symposium was really inspirational to me up here on the space station, even making this message in advance for you. So have a great day.
Okay, thanks very much. We're gonna start with some questions. Let me start off with a question here from the panel. Here, we're celebrating the 50th anniversary of spaceflight, MIT's 150th anniversary. Looking out the next 50 years, say you're a student sitting in the audience right now, interested in exploration. What advice would you give? Areas of endeavor that would be interesting to go into to set yourself on a path for exploring? Jim, do you want to start off?
Well, I having sort of stumbled into robotics, I guess I am a strong believer in robotics, not necessarily because I believe that everyone should be a roboticist, but because I think it forces you to deal with some really tough problems. So I think automation is going to be key to a lot of the things we do, whether it's a robot that you're automating or whether it's systems that humans have to use. I would say that one of the other really large challenges revolves with understanding how to engineer complex systems. So system engineering, I think, needs to fundamentally change. We spend, the cost of the system as the complexity goes up, that cost goes up almost exponentially, yet we're going to depend on very complex systems. How can we make them more robust? How can we understand their failure modes? How can we develop new tools for designing these systems in ways that we have some confidence they're going to work when we need there. So I think that from a research perspective, there's some tremendous problems out there, most of which, a lot of which have to do with understanding how to deal with complexity.
Great, thank you. Steve?
Well, Jim already hit two of the three I was going to mention. I think autonomy and systems engineering are right near the top of my list. The third one is something that I touched on already, and that's propulsion. I mean, right now, we get into space, for the most part, using pretty much the same technology that was developed at Peenemünde back in the 30s. Okay, we're still using chemical rockets. You just bought one yourself, as a matter of fact. And it's incredibly inefficient. I mean, the way we get into space is inefficient. The way we do deep space propulsion is horrifically inefficient for the most part. Now we're developing more advanced forms of in-space propulsion. Some of the ion propulsion techniques that are being used now enable us to do things we haven't been able to do previously. But I really think that, yeah, the third one that I would add to those two would be advanced propulsion systems to bring the cost down and the capabilities up by not factors of 50%, by orders of magnitude. We have to do that. I mean, space is just too big a place not to do that.
Great, thank you. Buzz?
I think we can learn a lot more about how to solve the problems of transporting people in more efficient ways, people or cargo. And I think the key to that really is reusability. Just as John Houbolt came up with a way of breaking down the spacecraft that are needed to accomplish a particular task with specialized spacecraft, I think we can also look at even further improvements. A little example that I was familiar with, back in 1984-85, there was some talk about going back to the moon for energy reasons. In the fuel crisis of 78, 79, cars waiting in line to get fuel, there was a good bit of investigation into the potential of solar power satellites. And the innovative additions to the classical way of wanting to have the solar power satellite at geosynchronous, so that as the Earth rotates, so does the satellite, and then it can be transmitting the energy that it collects with photovoltaic to particular spots, just like the beaming of transmission of weather conditions and TV and other communication devices. At that time, I was motivated to try and come up with an even better way of getting to the moon than with the specialized spacecraft. I thought, now, if I could develop a spacecraft that would find itself going continuously back and forth between the Earth and the moon, you can't just swing around the moon and come back to the Earth and then go back out again and expect to find the moon there. It's not there. It's going about 120 degrees around the Earth. But what you can do is three different swing-bys of the Earth can give you one swing-by around the moon on a free return, then a longer duration mission out, and then another one, and then intercept the moon again and swing around it and continue doing this. This gives you a pass by the backside of the moon. There are other ways of going out and as you're coming back in again, intercept the moon, now swing around the front side, and it takes you back out and around. Combinations of these can deliver people from the surface of the Earth to the surface of Mars, but it's very inefficient in comparison to the more classical specialized spacecraft of Apollo. And so when this was pointed out to me, my ego was really crushed. But I did know that even though it's not good to take people from the surface of the Earth to the surface of the moon, because it's a big investment, and you're not on this cycler for very long, 3.5, 4 days, if you're making the swing by the backside of the moon. I did know that it was good for adventure travel at some point. The administrator of NASA, when we went to the moon, Tom Paine, had an office in Santa Monica, and he was writing memoirs about submarine service in World War II. And but he continued to look at future missions, and he said, "Buzz, why don't you look at Mars? I know some people are looking at sort of resonant ratio of periods. The only trouble is it takes 5 or 6 of these things going around to get a selection." But I did another seat of the pants type operation, which I did here at MIT, fooling the faculty into giving me a doctorate degree when it was really taking what fighter pilots do, which they're not that smart. They have to break it down into basic things, and when you do that, you come up with some pretty good intercept techniques. So I applied that same sort of thing in 1985 and came up with cycling orbits between Earth and Mars. And every one of you here, if you haven't heard of NIH, you better learn what it means, because it's not National Institute of Health. It's not invented here. And if you're on the outside and you have a clever idea and you go and try and take it to the government, they're supposed to come up those ideas, so they're not going to welcome your new ideas, and neither are corporations, because they're supposed to do that. What we need is a way that motivates the stovepipe around government and around corporations, that creates an incentive for them bringing people in from outside instead of the lawyers having to sign releases and so forth to keep from getting sued. Reusability, I think, if you ask big rocket companies, what about reusability? They'll say, oh, well, it depends on how high a flight rate. What big companies really want to do is sell rockets. And the more they can sell and throw in the ocean, they're obviously motivated to do that. Just like what I indicated earlier, that the motivation to put a crew in the booster was to get more money out of each rocket you produce until you break the system and it gets canceled. But I really think that reusability and novel ways of doing things, design reference missions from NASA for going from Earth to Mars, I imagine there was not much on the Martian surface, maybe a few unmanned missions that looked at things, and then they put together a big armada, and everything goes from Earth to Mars, and when you get there, you have what you need to stay there for a while. Well, that's most inefficient, but if you can assemble things on the surface of Mars in successive periods, I asked Steve a while back, in using Phobos, I want to land a habitat at a certain choice location, and he says, well, you just tell me where you want it, and I'll put it right where you need it. Well, we do need things like that, but the design reference missions of NASA, until very recently, never used a moon of Mars to assemble things on the surface. They never used cycling orbits. The craft that the crew was in launched from the surface and got into orbit, and then that same craft went all the way to Mars and waited around while they're on the surface and became what's called the Earth Return Vehicle. And when it came back, it entered the atmosphere directly and plunked in the ocean. Well, that's hardly specialized. You'd like to reuse something. When it's put into orbit once, you'd like to be able to reuse it without having to go through the launch environment.
Okay, Buzz,
They're beginning to get smart in headquarters and not and getting into more reusable.
Okay, great, thank you.
That was not answering the question, was it?
We'll try another one. Okay, we've got a question for Steve here. As the rovers spend more and more time on Mars without finding solid, and that's underlined, direct or indirect evidence for life,
Right.
does your belief in the chances for life on Mars increase or decrease?
I think as a result of the rover mission, my view of how likely it is that life could have evolved on Mars has increased. The rovers themselves, this set of rovers was never designed to look for life or evidence of it. They're not fossil hunting machines. That's a very, very complex task. If anything like that exists, it's probably at a microscopic scale. We don't have on our payload the ability to detect organics, and so that's, hunting for fossils or life was never something we set out to do. What we did set out to do was to look for evidence of conditions that would have been suitable for life, and we have found those in abundance. And so my view is that the prospects for there once having been life on Mars are good enough that it provides a compelling motivation for future exploration, including the sample return mission that I talked about, including sending humans there.
Yeah, so I'd like to add that one too. I think I can say something about this. What was brilliant, I think, about the rover mission was that it asked a specific question and tested the hypothesis to look for definitive evidence of ancient water, and selected a payload which very specifically went after that hypothesis, and it was immensely successful in doing that. And I think now understanding the context for the fact that ancient water existed on the surface, that it persisted on the surface, which is clear from the stratigraphy, that it occurred in more than one place on the Martian surface. You were 2 for 2 in terms of locations where you decided to search for ancient water, and the evidence was found that was definitive, because I think the chemistry really did speak for itself. It was not a subjective result. Indicated that water did exist in the liquid form on the Martian surface for an extended period of time. We understand the pH range that happened. It's rather extreme, but parallel work on Earth about life in extreme environments has shown life forms that can survive. So I actually think the rover missions have increased the possibility that life could have existed.
I'd like to quote Steve.
Okay.
The Spirit and Opportunity were built to last 90 days.
Yeah, that's when the warranty expired.
Right. Yeah. And they've been around for 5 years, and one of them's not there anymore. But he indicated verbally and in writing that what they have accomplished in 5 years, and one is on one side and one is on the other, and I'm maybe bending it a little bit, but if there was somebody controlling those spacecraft in orbit around Mars instead of at Earth, where the transmission time round trip of controlling something is 4 minutes out and 4 minutes back if it's at the closest, and 20 minutes out and 20 minutes back if Mars and Earth are on the opposite side. But if you're there, Steve is quoted as having said that what they did in 5 years could have been done in 1 week. 1 week for what they did. And of course, they can do much more ambitious things when you're directly controlling them instead of the very conservative instructions that are sent once a day. And if it gets into trouble, you stop, figure out what the problem was, and then try and fix it.
Now, Buzz, you misquoted me,
Okay.
but you did it in a correct and constructive way for the following reason. What I actually said was that what those 2 robotic explorers have done, remotely operated from Earth in 7 years, what I said was 2 humans on the surface could have done in about a week. However,
But you got to have one on each side.
However, you are quite correct that if you robotically operate them from near Mars space, you will get much more done. To this day, the world record for the greatest distance traveled across the surface of another planet is held by the Soviet Lunokhod rover that was operated in the 70s, and that was joysticked from Earth. And the reason they could cover far more in a matter of days than Spirit and Opportunity have done in 7 years is because they were operated in exactly that fashion. So you're correct.
I'd like to just add another thing, because a workshop has just been formed out at NASA Ames called the International Lunar Research Park that's at the moon. Now it has to get there, so the way that I surmise they're going to do this is the big island of Hawaii will be a trial landing of the prototypes of what will be on the moon, and mock-ups of that can be done in NASA Ames, and the whole process kind of builds up and allows people to see what is being planned for the future. And you're not going to land everything at the same spot. You're going to land them at some distribution on the moon. So you have that same distribution, and you just place them there, and then you control them to come together and again, do what they're supposed to be doing. Now, that's exactly what I think we need to do from the moon of Mars, Phobos or Deimos. And now while you're here, I need to maybe ask you another so that I can accurately quote. What do you think right now would be the better controlling moon, Phobos or Deimos?
Probably Deimos, actually, because I need to think this through a little more carefully. But they're both close enough that you can real-time joystick. Yeah. There's no difference in terms of their distance. But for any given location on the surface, because of its longer orbit period, Deimos has a longer view period. So you'd actually be able to be above a certain spot on the surface longer from Deimos than you would be from Phobos. So I think
well, it's a little higher than Mars synchronous.
Yeah.
But you're going to need relay satellites in any event.
Yeah, if you've got all the relay capability that you need, and viewing is not a factor, then I'd go with Phobos because you get a better view.
Okay.
Conveniently, you just need 2 other relay satellites.
That would do it. Yeah.
If it was closer, you'd need more than that, but it just enables you to go in an equilateral triangle.
Okay, got a question for Jim here. What do you see as the biggest challenges or barriers to underwater exploration in the next 10 years?
Well, so something that I didn't really talk about too much was how sort of my view of the ocean has really been transformed over the last few years, and it's I think that going into ocean exploration as a physicist, I tend to look at the ocean as consisting of water molecules and salt and some fish swimming in them. And that's a really inaccurate view of the ocean, because the ocean's actually alive. Every drop of ocean water actually contains tens of thousands of microorganisms, and they're literally transforming the chemistry of the ocean at every moment, at every place. So it's very literally a living fabric, and it produces roughly cycles roughly half of the oxygen we breathe, that feeds the fish, and so on and so on. In other words, we depend on this. And the thing is that if I were going to be starting again, I think that I would focus a lot more on biology, maybe bioinformatics, because I think that those microbes really are sort of one of the key mysteries of life on this planet. They're everywhere, and we understand them so little. As a matter of fact, it's faculty here at MIT who have really pioneered the study. It's really the tools of genomics that have opened the window to this microbial world in the ocean. So I think there's tremendous links to this microbial world, to what humans are doing, to extreme environments like hydrothermal vents. They're probably the thing I'd look for if I were going to Europa. So I think, if I were kind of looking at the problems to tackle, it would be understanding in effect, how does this microbial world around us, particularly this microbial ocean world, work, and how do we depend on it, and how are we affecting it?
How do you feel we're technologically limited versus?
Most definitely. I mean, I think that in all of these environments, I mean, exploration is fundamentally a technological enterprise, and I think in the ocean especially so. I mean, one of the great things about the ocean, if you really like getting your hands dirty, if you like getting involved in this stuff and going to sea, I always say sort of, have robot, will travel, because you get to actually build your robot, and then there's nobody to hand it off to operate it for you. You got to take it to sea and operate it yourself. It's a very small enterprise, really at the moment. So I think that small research labs can make a very big difference. Individuals can make a very big difference. It's a small community now taking on really big problems, and it's actually really exciting times.
Actually, Maria, I've got a question for Jim, if that's okay.
Go for it.
You know, one of the things that we get into in the space business all the time is human versus robotic exploration, right?
Yeah.
What about human versus robotic exploration in your world? What about, you know, autonomous underwater vehicles versus Alvin and that sort of vehicle? What, if you have to divide up a limited research budget for such things, what's the most efficient way of spending the money?
Well, I think that, you know, our dominant human-occupied platform are really ships. And I don't think you will find an oceanographer on the planet who thinks we could do without ships. As a matter of fact, we all believe we need more ships.
Right.
Now, whether or not you are a believer in human-occupied vehicles or not, I think that all of us are believers that we need a portfolio of capabilities. So there's no, one answer. I mean, there's no silver bullet, right? That we can go buy and, if I sell you an AUV, you can go solve all your oceanographic problems. Of course, it doesn't really work that way. My oceanographic, my AUVs are good for some really simple problems. As a matter of fact, they're so simple, you would never use a human to do them because they're just not, worth the expense of having a person do it. On the other hand, they're a tremendous adjunct to activities that humans can carry out. So I see that remotely operated vehicles and human-occupied vehicles, there is a bit of give and take there, and I think that probably you had David Mindell up here. David Mindell, I think, has played a role in pioneering both the ROV part of that equation, but also using human-occupied vehicles. So I hope it never becomes a situation where we don't send humans down into the ocean. But when I have to think about where to spend my money, where I'm going to accumulate investment, where I'm going to accumulate capability, I think a lot of times from a technological perspective, human-occupied vehicles have kind of plateaued in a way in capability in the ocean, whereas ROVs are still very much on the increase in capability.
Yeah, let me ask a related question to that. One of the things that I think has been fascinating about exploration of the planets is that we've gone from a situation where the planets and the moons are just bright spots in a telescope to places where we could visit or imagining visiting, and that because of various limitations, we've had to be extremely judicious and arguably smart about how we design experiments to go explore. Are there lessons from or examples of things that we've done in the exploration of the planets that could help us in the exploration of the oceans or remote places on Earth?
Well, I will say that we deal with the robotics community and the technical community in the space sciences all the time. So we see them as kind of kindred spirits. We have very different sets of thresholds and economics that we deal with, but they've got a lot of money to spend on solving problems, a lot more than we do. So just to give one example, I think that one of the things that really limits robots is their perception capabilities. So right now, I think at the onboard decision-making, we can actually make really, there are people who can do good onboard planners. The problem is feeding it with the right information with the environment, and that's the ability to interpret that video camera image or sonar system or laser line scan system to be able to understand what's going on in the environment around it and understand how that relates to the robotic system. And I have this feeling that we're sort of on the cusp of big changes in that world, and that will have enormous implications for autonomous robotics. And I think those are more likely to come out of NASA than they are to come out of the space sciences, or rather the ocean sciences. And when they do, we'll grab them.
I'll give you an example from my own experience. Some years ago, I was involved in some research in Antarctica where we were studying sedimentation in ice-covered lakes as it might relate to sediments being deposited in lakes on Mars. And there are these lakes in Antarctica with 5 meters of ice, and we wanted to study the sedimentation process in the lake bottom. We had 2 tools for doing that. One was a remotely operated vehicle, and this was a great thing. You could put it down a dive hole, and you could sit there with your mug of coffee, and you could sit there for hours with a generator running this thing and explore the lake bottom. And then the other was scuba equipment, where we'd actually go down the lake ourselves. And what I found when I did this was that the robot was really good for answering the simple, easy, first-order questions of what the environment was like, but that I didn't really feel that I understood the environment well until I was down there myself. The human brain, hand, eye system is very good for formulating and testing hypotheses right on the spot in a way that's much more difficult to do with a robot. What the advantage of having that robot down there first was that because I gained this first order understanding of what the environment was like, you go down there and you're doing a dive, you're doing an EVA, and you've got a half an hour of bottom time. You want to use that half hour very, very efficiently, and by having gained the first order information, you could plan your activities and you could really get things done much more efficiently than if you didn't know what you were doing when you first went down. So it sort of taught me two lessons. One is that humans do best when they are aided in advance by the knowledge that robots provide. But the other is that when you've got a limited amount of budget to spend, that robots are a good way of doing it. So I think human robotic precursors to humans is the way we're doing it is a very logical way, and that experience, I think, sort of shaped my view of that.
Mm-hmm.
I think the fact that a good bit of our EVA spacewalking experience recently is being done by oceaneering is not just an accident. I was the first astronaut to really train underwater in neutral buoyancy that simulates floating in space with zero gravity. It's not too good to simulate the movement around on the surface of the moon, but it really is a great aid for long-term activities of getting a pacing of what can be done in a particular time period. The zero-gravity airplane gives you 25, 30 seconds. And a lot of that can be kind of misleading and cause a lack of appreciation for materials and their effect, or the total time span of accomplishing a particular task. But I went down on the Nautil French submersible to look at the Titanic, and you can kind of analyze that from a surface perspective, and you know the numbers that are all involved. But when you're in a submersible and it takes an hour and a half to sink 2 miles down in the ocean, but you lose the ability to see anything at about 400 feet because everything is dark. You begin to get an appreciation, and I'm very proud of being a charter member of a group called the Sea Space Symposium, and we exchange technical information of the similarities of those two environments, and we also enjoy diving wherever we have these meetings.
Well, I'll add something to this as well. Something that I think that the planetary community has done well is the approach to exploration, where in the planets we start with a flyby of a planet, then we move next to an orbital reconnaissance, choosing a suite of sensors to do a global characterization, and then on the basis of that global characterization, we then can choose a lander to go to a place of particular interest. And in fact, it was global orbital thermal emission spectroscopy that led us in particular to the Opportunity site on Mars on the basis of the detection of the mineral hematite, which can form in various ways. And one of the ways, the most interesting way that it can form is as a precipitate from water. And but you don't have an understanding for what the mechanism of formation is until you see the geological context of it. And of course, the in situ observations from the Opportunity rover did indeed show that it formed in that most interesting way.
Yeah, you know, if I could just sort of add to that, I think that one of the very big differences between the ocean sciences and the space sciences is that the space sciences are really run as big science, and the ocean sciences are still largely independent PI science. And as you all know, there's a really big difference between that. And as you get to sort of a larger scale enterprise, you take on a whole sort of a formalism about process. You know, perhaps that you know, in an independent PI model doesn't work very well. And so I think that's maybe part of maybe what you're touching on there.
So it sounds like maybe you need a strategic plan for ocean exploration.
I just served on a National Academy panel actually for planning the ocean infrastructure for the next several decades. So it's exactly the kind of conversation that's going on right now. But it's not something you can do from top down. It's, as you know, it's a community initiative.
If you want a decadal study, Steve Squyres is now available.
Well, very much inspired by.
Well, I mean, one thing you need for ocean research is you just need a lot more money.
Yeah.
I mean, I am, you know, as someone who has been a beneficiary of the enormous amount of funding that NASA gets to spend on space exploration, I look at what's spent on ocean exploration, and it just seems wrong. I mean, you guys, you know, this is the planet that we live on, and yet you look at the money that's spent on exploring the ocean, and it's a pittance. I had the chance once to go on the cruise on the Atlantis II and do a couple dives in the Alvin. And I remember while I was out at sea, and they operated that whole, I think that whole ship in the Alvin was done for like $20,000 a day or something. It was phenomenal what that thing has done. And at the same time I was on that cruise, I was on the review board for some proposals for the Cassini mission to Saturn. And so in between dives, I was reviewing these Cassini proposals. And we're sitting on the ship at night, one night, and the guys who run this fantastic Alvin for $20,000 a day asked me, well, how much does this Cassini mission cost?
Ooh.
I thought I was going to walk the plank.
Yeah.
I thought they were just going to toss me over the side. When
There was no way to finesse that question?
No, there was no easy way out of that one. And you know, but truly, you know, I think it's an area where we've got to be spending a lot more money than we're spending now.
Yeah, well, with that in mind, I have a couple of questions here that I think I can put together and have people comment on. The first is, does the government have an obligation to fund exploration? What's the future role of commercial organizations in exploration? Does the private sector have an incentive to fund exploration? So, would anybody like to comment on that?
Try tackling just the first one. Does the government have an obligation to fund exploration? My answer to that's actually yes. You know, I think that in a society that is as wealthy as ours, where our government is able to do, and our economy is able to do a pretty good job, not a perfect job, but a pretty good job of addressing the basic human needs of our citizens, that we have a certain obligation to spend some fraction of our resources on things that, you know, for lack of a better word, enrich the human spirit. For things like the arts. Do we have an obligation to spend money on the arts? I think we do at some level. You know, basic research that might not pay off in tangible ways for hundreds of years. And exploration, I would put all of those in that category. I think there is an obligation because, you know, we're here to do more than simply survive.
Great. Buzz, do you have any thoughts?
Commercial stuff.
I found that looking at overall national space policy, we need to integrate those. And I found it convenient to, well, I was prompted by the previous administration's vision for space exploration. And I said, gee, we have to do more than just explore. This is when you're thinking about, what are you going to do at the moon? You're going to go explore again? No, you need to develop what you've explored. And then I found, well, it's more to it than that. You'd like to make that a commercial for profit, reduce the cost of doing things by having it have a payoff to it. Now, in addition to exploration, development, commercial, you would like to maximize the science return. And if what it is you're expending resources on is not enhancing the security of the nation, So I found few people could come up with an addition to that, exploration, development, commercial, science, and security. Sometimes people will say, well, how about education? Well, each one of those categories has education, the fundamentals that lead to it. And I think we've identified those pretty well in the ones that we need to correct as a nation with STEM, science, technology, engineering, and math. And I think many of the things we do for exploration better establish a balance between education and exploration and these other things that we do.
So having founded and sold a little robotics company, let me kind of take this from the commercial perspective. I guess the way I look at this is sort of split in two domains. One is time windows. So, you know, if you're a big publicly traded company, you respond largely to the quarterly report. If you're a startup that's venture capital funded, you maybe respond to the time horizon of the investors, which might be, if you're really lucky, a half a decade, but probably much shorter than that. And those are kind of the planning horizons in a way that you have in the commercial world. It's driven by when the investors want a return on their investment. And there's not a lot of people who are willing to put their money in and say, it's okay, don't give me anything back for 30 years. So I think that that's one way to kind of articulate where government needs to step in. Government needs to look at the long time horizon issues that aren't sort of naturally addressed by the commercial sector. Now, having said that, I think that the government does have a role in fostering and developing a commercial sector that can step in when those become viable. And how exactly it does that, I think, is probably something that is still sort of a process of discovery. I don't think we have that one right. And there's some things that, by the way, don't make sense to transition. I think that personally, and I may, you know, at least in my little domain, in my little ocean world, I think it doesn't quite make so much sense to transition something when the government is in effect the only customer, and there's really one customer. You know, we've had some experience with trying to do that, and it hasn't always worked so well. You know, you need to have sort of a scale of operations before you know, where you can actually have some competition out there before that works well. So those are kind of my takes on that problem.
Okay. Well, let's move into something that's perhaps a little bit related, and that is the area of manageable risk in exploration. We don't take easily to large endeavors where people are lost. The Titanic sinks, we're still talking about it. But yet, 1 in 10 people who climbs Mount Everest doesn't make it. And that seems to be acceptable for some reason. What is the right balance of manageable risk in exploration, especially at a time when we're thinking about commercial space? We could be thinking about commercial ventures deep in the ocean. Right, what's the right balance?
Well, I think a lot of it has to do with how things are funded. I think if Everest expeditions were publicly funded, I think a death rate of 1 in 10 would be something nobody would find acceptable. But it's a case where individuals, through their own choice, decide to go out and do it, and they take the risk knowingly, and they take it on. And I think the analogy in space is going to be that when corporations and individuals are willing to risk their own assets and their own lives without government support, that higher levels of risk are going to be tolerable. But you know, even robotic missions, the robotic missions that we carry out, they're funded with government money. I know that a chance of failure. I mean, we talked a lot about probability of failure when we were talking about landing Spirit and Opportunity on Mars. We recognized that on the launch that there was you know, roughly 1% chance, something like that, 1 to 2% chance that we could lose the vehicles then. But a 1 in 10 chance of a failed landing was deemed unacceptable. by NASA headquarters, even when we had 2 vehicles going. So the government is extraordinarily risk averse, and that has been historically the case.
Well, I know for, I believe for Spaceship One, I know for commercial space, there was at some point an attempt to impose commercial flight requirements on that, which of course would have bankrupted the whole operation, because you can't guarantee that level of safety. And that was a privately funded enterprise.
Right.
So I think most people feel that would be pushing it too far. So. Buzz, any thoughts on this?
Well, I look at the number of people killed in automobile accidents. They've been around for a long time, but compare that with aircraft accidents and space accidents. The high visibility and everything is more and more visible these days because of the communication industry. And I think they've had a tremendous impact on the acceptable risks.
Visibility does indeed have a lot to do with it. I remember in the late 90s, there were 2 Mars missions that were lost in succession. The Mars Climate Orbiter and the Mars Polar Lander. Polar Lander crashed on the surface. Climate Orbiter burned up in the Martian atmosphere because of a mix-up over English and metric units. It's a very bad way to lose the spacecraft. Don't let it happen to you. I remember it was either Time or Newsweek in their end of the year summary that year when they're writing about NASA. They called that NASA's worst year since the Challenger accident, which I thought was ludicrous. I mean, these 2 missions together cost like $500 million. I mean, that's something like 3% of the NASA budget over the time in which they were developed. And they were comparing that to the loss of a shuttle and 7 lives. It was crazy. But the reason they put it that way was because these were missions to Mars. And that's the same reason that the very, very risk-averse attitude was taken towards our rover missions and every Mars mission. Anything that is that visible, it's really directly related, you're right, to the visibility of the enterprise. And when the visibility is low, you can get away with stuff, but when the visibility is up there, you get a lot of scrutiny, a lot of help.
Okay, Jim, I've got a question for you here. What comments would you offer about the importance of exploration of the oceans for solutions to the challenges we have with food, fresh water, and energy?
Well, let's see. I guess first of all, I would say that I think what's going to happen is we're going to be increasingly turning to the ocean for solutions in those domains. So it's true that we fished out the ocean. A marvelous slide that I have, by the way, which I didn't show, shows sort of the rate of domestication of species as a function of time. And what you find is in the terrestrial environment that rate of domestication, kind of started about 10,000 years ago, and completed sort of thousands, not too many thousands of years after that, for all practical purposes. In the ocean environment, we are really just learning to domesticate species now. So the number of species which have been domesticated have largely been domesticated in the last 100 years. And so what you're seeing is that transition from hunter-gatherer to farming today, vice 10,000 years ago. And what's going to happen is there's going to be a lot of lessons that we're going to learn the hard way. As a matter of fact, we could recount some of those right now. So I think that what this really boils down to is trying to avoid making mistakes on really large scales, potentially unrecoverable scales in the ocean as we industrialize the ocean. So I think that, and that's kind of why I have this focus on the microbes. They're kind of the foundation of everything there. So I think that if you're going to take on, in effect, a set of ocean problems, I think that's. I'm not sure if I answered the question really there, but those are the directions I would go.
Great, thank you. Okay, so time is winding down here. I want to ask everybody one last question. What experiment would you like to do if you could pick one exploration project that you could do to cap off your career, what would you like to do, Buzz?
Human permanence on Mars. I mean, that, with the comparison of storytelling and visibility of people in comparison with landing brief periods on the moon, the people that land and stay on Mars are going to be much, much greater in appreciation by history. A nation or entity that makes a commitment to move human beings from this planet and to set up a settlement, a growing settlement off planet, is beginning to satisfy Stephen Hawking's warning that we've got 200 years to before we blow ourselves up or nature blows us up or something causes really major detrimental setbacks for humanity that could be prevented by having a growing, sustaining colony of people somewhere else.
One experiment.
One experiment.
Underwater exploration of Europa.
Of what?
Yeah.
Europa?
Oh,
Underwater exploration on Europa. That's the one for me.
oh,
Yeah.
that's a good one.
Yeah.
These are all.
Top that.
Okay.
Yeah.
Ocean guy?
Yeah, ocean guy.
Hard to make-
Well, I'll tell you what. Give me a call.
Yeah, we
Because that
should
one
talk.
sounds pretty good. Yeah. I guess the problem that we've been thinking about a lot lately, so that my colleagues and I, is how can we follow marine organisms and understand how they interact with their environment. And so it's a very organism-centric sort of perspective. Right now, we sort of tend to sample the ocean geographically in the same spot every time. We see different organisms there at different times. But actually understanding how these organisms are interacting with the environment, it's kind of like, you did all of your observations of deer from a deer blind and never figured out that, oh, they're actually going down to the stream to drink, and they actually migrate away, and they mate over there, and this is where they have their, have the fawns. We don't have any of that picture of most of these organisms. We don't understand their life histories at all. So I have this interest in building sort of robots that we call it the paparazzi project. So you're going to follow around organisms and snap pictures of them when they least expect it.
Now we could do that on Europa.
Yeah.
Mine would be deep drilling on Mars, because
good
if
one,
there's life on Mars, I believe that's where it's at.
Yeah, that's a good one, too.
And that one, well, I think we could do it. I'd like to see us do all these. That would be fantastic.
If indeed there were oceans on Mars, and something happened to cause them to freeze, now the atmosphere is such that the wind blows pretty high speed and is going to cover up the horizontal sea level ice. Wouldn't you expect that would be what you'd look for, is water, ice at a particular level that, I mean, once it freezes for whatever that reason really is?
I think what might happen actually is that because the Martian regolith, the soil, has been so pounded by impacts over time, it's probably very porous, very permeable, and a lot of it's just going to soak into the ground and freeze. And in fact, we're finding a lot of
different levels.
permafrost ground ice on Mars now. Yeah.
Okay, well, I'd like to thank our panelists here for a fascinating discussion.